So learning unit 5 is on equilibrium. And I promise you, if you learn this unit well, the next 2 units are going to be so much easier because they are applications of equilibria. So if there's ever sort of like a pivotal unit that's really important to understand well, this is it. So we're going to introduce equilibrium in this learning unit 5, and then in learning unit 6, we're going to talk about acid-base equilibria, and then we're going to move on and talk about more applications of equilibria and buffers and things like that in learning unit 7. So a really, really important learning unit. Videos might be a little bit on the longer side here, but I hope it really sets kind of the foundation for a solid understanding of how equilibria works. So what exactly is equilibrium and how do we want to think about it? We want to think about it as applying to kind of the extent of a reaction after an unlimited amount of time has passed. So for example, if we're looking at this reaction that interconverts this colorless gas N2O4 with a brown gas NO2, what we can see is that at early times, we can see we've got very little of this NO2 brown gas. But as time goes by, we get more and more of this brown gas. But you can see here, looking at these last 2 panels, we really haven't changed the amount of brown gas we have at that point. And that's because we've reached equilibrium. This is a really important concept to highlight. We're not saying that chemistry isn't happening anymore, but what we are saying is that the rate of the forward reaction, that is the conversion of the colorless gas into the colored gas, is happening at the same rate as the reverse reaction. These special arrows that we see here tell us that this is a reversible process. Reversible processes imply equilibrium. So we have to make sure we learn to draw these new sets of arrows when we have our chemical reactions. So a really important concept. We're not saying that chemistry stops happening. We're just saying that it has reached equilibrium. An analogy that I often like to give is imagine, that you've got a club that has just opened up, it's 5 o'clock in the evening. Early on, you're going to have more traffic going in than you have going out. Well, at some point, you've reached capacity of the club. And at that point, it doesn't mean that nobody's going in or nobody's going out. What it does mean, though, is that for every one person that goes in, somebody has to come out. And that's a state of what we call dynamic equilibrium. Okay. So it is really important, even though I introduced this concept of rate, when I said we're having the forward and reverse rates equal to one another, we do need to make sure that we don't confuse equilibrium and kinetics, or thermodynamics and kinetics. So when we think about equilibrium, that's this unit that's also thinking about things like enthalpy and entropy. That tells us whether a reaction occurs and how much product that we make. So these terms are important that I want you to kind of have up in your brain. We're going to revisit those at the very end of the semester. Kinetics, as we had in our last learning unit, that is about how fast something happens. So thermodynamics does not really tell us how fast something happens. It just tells us if we give an unlimited amount of time for a reaction to proceed, will that reaction happen and how much product will we make? So don't confuse kinetics and equilibrium. And as we saw in our last learning unit, when we had the discussion of kinetics and we talked about drawing these reaction coordinates, we can see that the activation energy really tells us how fast a reaction proceeds, and then the difference in energy levels between the reactants and products, as we're going to see here, that tells us how much product we make. So these are related, but they are different and distinct. All right, same generic equation that we had when we wrote a rate law. Now we're going to write, or a rate expression. Now we're going to write an equilibrium expression. So here, coefficients, like we had with rate expressions, do matter. And we're going to use a different K. We're going to use a capital letter K. We're going to call this big K. This is the equilibrium constant. And the equilibrium constant is equal to this hot mess. So I'm going to tell you what this is. What we do is I want you to have in your brain products over reactants, products over reactants, products over reactants. That's how we write an equilibrium constant. And what you do is you multiply the concentration of products raised to powers that are coefficients, and then you divide that by the product or the multiplication of the concentration of reactants raised to powers that are coefficients. So notice how that's different from when we wrote a rate expression, right? We still used coefficients, but they were fractions. So one of the skills that's really important to understand here is how we write these different pieces, okay? So this is an equilibrium expression. You'll note here that we're going to be using equilibrium concentrations. This will come into play as we get to the very end of this video here. So two rules that we have to think about when writing, or as we'll see in our next slide, manipulating equilibrium constants, is we do use coefficients in our balanced chemical equation. They become exponents. The second rule here is when we're writing equilibrium expressions, if you have pure solids or solids or pure liquids, they do not appear in your equilibrium expression. So if you have water, not water as a gas, but water as a liquid, you won't see that. Any solids, any salts, or anything like that are not going to appear in your equilibrium expression. So we'll practice doing some equilibrium expression writing in class. A couple of other things we want to think about, and in the accompanying notes for this first skill here, I have kind of a comparison with how we think about this with Hess's law. So I'll sort of say that here, but it's not written in words here. We can manipulate equations, and we can manipulate equations that have equilibrium constants. So what we need to do is think about, well, when we add equations, what do we do with equilibrium constants? So again, if we sum reactions together, noticing that things like the C here, which is an intermediate, will be canceled out, we get an overall reaction. That was like what we did when we did Hess's law. But while in Hess's law, we added up our enthalpy values, here we multiply together our equilibrium constants. So make sure that you can compare and contrast how we manipulate equations and handle the associated sort of parameters or properties of those equations. We handle them differently for enthalpy than we do for equilibrium constant. So summing reactions, we multiply equilibrium constants. If we reverse a reaction, remember with enthalpy, we just put a minus sign there or took the negative of it. For this, we're going to take 1 over. It's going to be the reciprocal of it. And lastly, scaling up or down a reaction. If we scaled a reaction up or down with its reaction coefficients, we use that same scaling factor to change the enthalpy value. So what's different here when we have a scaling up or down of a chemical reaction that has an equilibrium constant, that scaling factor becomes an exponent. So really key here is making sure you understand how to manipulate equations and then their associated equilibrium constants. So again, we'll practice some in class with that. The last thing to think about when it comes to manipulating equilibrium constants is representing that sometimes when we have gases, we can represent concentrations as molarity, moles over liters, or with gases, we can use partial pressures. So we need to be able to understand if that equilibrium constant is an equilibrium constant using molar concentration or if it's partial pressures. Again, this really only comes into play if we're talking about gas reactions. But what we can see here is an equation, again, that'll be provided for you that allows us to interconvert between equilibrium constants that are based on partial pressures and equilibrium constants that are based on molar concentration. These are actually the same equation here, right? But what we have is we're just sort of changing that sign there. It's just solving one for the other. But the big thing that we need to figure out is how many moles of gas are different between our reactants and our products. So we literally need to have a balanced chemical equation that we count number of moles on the reactant side, count number of moles of gas on the product side. We always do deltas as final minus initial, products minus reactants. So the number of moles of gas that are a product minus the number of moles of gas that are a reactant. Now, one of the things you'll notice is if you have the same number of moles of gas on each side, your equilibrium constant doesn't change. But you might have a situation where it does change and you have to know which equilibrium constant you're using. All right, so lots of little things, theory and kind of some small calculations that we're working through here. All right, this last little bit is conceptual. How do we think about equilibrium constants? I want you to think about equilibrium constants and I want you to relate it to a number line, right? You learn number lines in elementary school. Small numbers are on the left, big numbers are on the right, okay? So what I want you to be able to think about is mapping a number line above top of your chemical equation, right? And then ask yourself, where does my number sit? And let's go through a few examples here. Take this first chemical equation that has a very small equilibrium constant, right? Part of what we need to be able to do here is recognize that this is a very small number because we have a negative exponent there. And then this is a very large number because we've got a large positive exponent there. All right, so if we have a very small equilibrium constant, small numbers live on the left of my number line. So that equilibrium constant sits above the reactant side of my equation. So that tells me I favor my reactants. And looking at what we have here from a pictorial standpoint, if I'm just interconverting blue and red molecules, I have mostly blue molecules here. That makes sense. My equilibrium lies on the left, on the reactant side. Flip side is true here when we have a large equilibrium constant. Large numbers live on the right side of my number line. So if I put that over my chemical equation, that's sitting over my product side. So I'm going to have mostly product. I would be product heavy here. Now, what happens if you have an equilibrium constant that's closer to 1 or unity? Well, in that case, you have pretty much equal amounts of reactant and product. So that's how I want you to be able to think about equilibrium constants. Small numbers favor reactants, large numbers favor products. It's easy to think about this as sort of being like a teeter-totter or a seesaw, right? If we've got sort of products and reactants on two sides of a seesaw, we can sort of tip what we have here. And that's a great analogy to help us understand how some things are working here. But I want to reconcile two myths that students often have when they use this analogy. The first is that a teeter-totter wants to be here. And that's not necessarily true. Every chemical reaction has its own equilibrium constant. For some reactions, it might be here. For some reactions, it might be here. And for some, it might be here. But an equilibrium constant of 1 does not necessarily represent where every reaction wants to get to, an equal amount of reactants and products. It's unique to each reaction. Nothing you can necessarily predict, but it's important to understand that those are sort of distinct. The second is that we write equilibrium expressions for the reaction as written. If you reverse the reaction, remember we take 1 over that equilibrium constant. So if we had a large equilibrium constant and all of a sudden we reverse the reaction, then it would be 1 over that very large number. That would be a very small equilibrium constant. So equilibrium constants are for the reaction as written. All right, 2 important myths that we need to make sure we sort of reconcile so students don't have a misunderstanding of how equilibrium works. All right. Last couple of slides here. So an equilibrium constant really represents where you want to be. We're going to identify something that we call Q. And Q represents where you are. Okay? We're going to still write it very similar to what we wrote when we had an equilibrium expression. It's still the product of the concentration of products raised to powers that are coefficients, divided by the product or the multiplication of concentrations of reactants, raised to powers that are coefficients. But what's different is the values that I put in here are the snapshot of where I'm at any particular time. Let's say that our teeter-totter wants to be here. That's our K value. But if my teeter-totter is here, this is my Q value. And what my reaction wants to do is shift so that it gets to be where I'm at my equilibrium. Okay? So this has to do with what we call equilibrium shifting. Okay? So this Q versus K comparison, just highlighting the difference here. K represents equilibrium concentrations. Our teeter-totter is where it wants to be. So we are going to have a relative distribution of products and reactants that reflects that equilibrium constant, highlighting that it might be a small number, it might be a large number, it might be a relatively equal concentration of reactants and products, a relatively an equilibrium constant that's close to 1. All of those are plausible scenarios for any given reaction. It's unique to that reaction. Q represents where we're at. It's a snapshot of the concentrations that we currently have. Now, as we're going to see on this last slide that sort of wraps everything up, we're either going to be reactant heavy, meaning the reaction has to move forward, or we're going to be product heavy, meaning that train needs to turn around and convert products back into reactants in order to get to our equilibrium mixture. Okay, so 3 little kind of pieces here. I'm going to zoom in and kind of show each one individually so we don't sort of get overwhelmed here. But let's imagine this first scenario here. If my Q is less than K, Q is less than K, that means I'm to the left of my equilibrium point. We can just look at this like our number line. Q needs to move to the right so that it overlaps with K. So what we'd say in this situation is my equilibrium needs to shift towards products. My reaction needs to go in the forward direction so that Q becomes K. Okay? I would be reactant heavy in this situation. I would say my reaction would shift right, make more products. Let's go on the flip side. Let's imagine that Q is greater than K. In that case, we're more on the product side than we're supposed to be. We'd say that we're product heavy. In that case, our reaction would need to shift left. We'd actually need to do the reverse reaction and make more of our reactant in order to reach our equilibrium mixture. Now, if Q is equal to K, that's where both of these reactions are trying to go. Both of these situations are trying to have Q equal to K. And if Q equals K, then you are at equilibrium. So one of the things we'll realize as we begin doing equilibrium problems is that this might be one of the first questions we need to ask is, where are we at? Where do we want to be? And how does our reaction need to shift to get us there? All right, so that's our first introduction to equilibrium and talking about equilibrium expressions.